This is NCCER Instrumentation 2, Module 2. Instrument Fitters Math. So, trade terms, I feel like you guys should know that. You should know that a right triangle is 90 degrees. I feel like they pushed the line segment trade term in here a bunch. A straight line that has a starting point and an ending point. And hopefully everybody knows what a triangle is. My first highlight is in the second paragraph in the bottom left of page 1, third sentence. As much as possible, the bends should neatly follow existing contours such as pipe racks, structural beams, process control lines, piping elements, and other types of structures. This is talking about bending tubing and stuff like that. You got we have a presentation tomorrow from Rosemount. Guys coming to talk about pressure transducers. Should be pretty good. Next Wednesday, we have a guy coming from Swedgelock. As far as like the tubing and connections and standards and stuff like that, they are it. Like they are the primo brand. It's like Fluke or Allen Brad. Like they're kind of the brand that there's other brands, but they're the best. And the guy's good at talking about stuff. But y'all are gonna do some offset bends and stuff like that. So like you have math to be able to do this stuff, but if it's going to be, I mean, has anybody done any tubing at all? Done a little bit? Like, actually had to use like a lever bender and stuff at work? Okay, so this stuff will help. I feel like, in my opinion, tubing is easier than conduit. Mostly just because it's in my hands and stuff like that. Most of the...
it's easier to mess up though.
It's easier to mess up, but it's also...
easier to fix.
Like, I feel like you can just like bend it with your hands a little bit back, and then they have like I have the spring benders that help keep the shape if you're bending it just by hand and stuff. But yeah, this is tube bending and stuff like that. That's a chapter that I teach that I never did. I was an industrial electrician that did instrumentation stuff as well. But tubing and stuff, we never had we probably could have done it for like actually that might have been a maintenance thing, but the installers would do the tubing and whatnot. But it's good to know, in case you have to like fix something, it's good to have that. Circles and angles, 110, second paragraph. I got 2 questions coming from, I got everything highlighted except for the last sentence. Bending a straight piece of material creates such an angle as illustrated in figure 2. A straight line segment with a starting point and an ending point has 180 degrees inside or interior degrees from a point to point as shown in figure 2. This next sentence is what I really keyed in on. If another straight line segment is connected to either point and continues on the same plane as the first line segment, the interior degrees remain at 180 degrees from point to point as shown in figure 2. If the connected line segment is rotated up or down from the connecting point, the angle is formed. An angle is formed that has less than 180 degrees in it. So that's pretty much saying you have a line. This is 180 degrees, right? If you have 2 line segments that are connected right there, and one of them goes like this, and then the other one takes an angle, you're going to have an angle that's less than. No, that's not less than. Less than 180 degrees. As you can see in figure 2 on page 2. So, I don't know why I drew it. Straight line segment, 2 straight line segments, still 180. If you make a bend, it's going to be less than 180. Page 2. Second sentence on page 2 is highlighted. The degree of the bend is determined by where the fitter wants the bend of the tubing to go. Duh. Like, that's such a stupid line. Last sentence in that paragraph is highlighted. Applying fitter's math is nothing more than making use of the relationships between the degrees of the interior angles and the lengths of the line segments for tubing. polygons. I'm just gonna keep going, I know.
I feel like I'm gonna do bad in this test. That's usually the case.
Easier stuff to do that.
It just doesn't make sense in my head.
Polygons, second sentence through the end of the paragraph. A polygon may also have another name based on the number of straight line segments the figure has. For example, 3 line segments form a triangle, 5 line segments form a pentagon, 7 form a heptagon, also called a septagon, 9 line segments form a nonagon, 10 line segments form a decagon, and so on. Next paragraph, first sentence is highlighted. If a line segment is bent at angles until the 2 ends connect, the figure formed will have the same number of separate line segments as the number of interior angles. So all that's saying, if you look up here on the board, got your stop sign octagon right here. I've got 8 line segments, 1, 2, 3, 4, 5, 6, 7, 8, and then I also have 5 interior angles. 1, 2, 3, 4, 5, 6, 7, 8. Good? I have the hexagon in figure 3 highlighted. You should know all of these, but you should know all your polygons probably up to 10, right? Yeah. Because they're just gonna, I think they just show you one of them and they say, what is this, as far as goes. But I've got that one highlighted.
Wait, which one do you have on?
The
Gotcha.
hexagon, 6 sides. Page 3, the third paragraph on the page, last sentence is an online test question. When all the sides of a polygon do not have equal length and all interior angles are not equal, the figure is called an irregular polygon. So that would be like these.
Over.
Irregular. So no equal angles, no equal angles, no equal line segments. 130. First sentence. I got like 3 questions that come out of the first sentence. A triangle is a 3-sided polygon with interior angles that total 180 degrees. Next paragraph, second sentence to the end of the paragraph is highlighted. An equilateral triangle has all line segments the same length as shown in figure 6A. Isosceles has 2 line segments with the same length as shown in B. And a scalene triangle has 3 line segments of different lengths as shown in figure 6C. This is a triangle, total of 180 degrees.
You're back in 9th grade?
This is, it's funny because I teach a lot of, the math in the core class is a lot of the same math my wife teaches 4th graders.
Yeah.
And I have a lot of people that struggle.
I would say who fails? Dustin.
That's horrible.
You got an equilateral triangle. An isosceles triangle that has 2 that are the same. So A to B is 4, not A to C. A to B is 4, A to C is 4, and then the third side is different. The hypotenuse is different for an isosceles. And then a scalene has all different sides. The paragraph in the top right of page 3, second sentence, just the beginning of the second sentence. You just need to know a right triangle has 1 90-degree interior angle. So this is a right triangle. This is where you do a lot of your math from a right triangle. But a right triangle has 1 90-degree angle. Flipping over to page 4. So the triangle section, the sentence that splits the columns is highlighted. As will be discussed further in this module, as this module progresses, the right triangle in particular forms the basis for bending tubing because of the relationship between the sides and the angles of the triangle. I'm going to keep going and give y'all all the section reviews and stuff just for the end. Section 2. working with right triangles. 210 right triangles all the way at the top right of the page. The first sentence in that top right paragraph on page 6. It is standard to identify the different line segments of a right triangle with small alphabetical letters. B is usually associated to the base line segment. So I didn't highlight all of them, but B is usually the bottom one or the base. A is the one going vertical, which stands for altitude, and then C is always your hypotenuse. Last paragraph before 211, whole thing is highlighted. A mathematical term that's used to refer to the slanted line segment C, the right triangle, is hypotenuse. Remember it as a line segment that is directly across or opposite of the right triangle. Hypotenuse will always be opposite of the right triangle. Pythagorean theorem, 211. I've got the third sentence through the end of the paragraph highlighted. His proven right angle theory, which is still valid, is the Pythagorean theorem. What he proved was that in a right triangle, if you square the length of the line segment directly across from the right angle, the answer will be the same as adding the squares of the lengths of the vertical line segment and the base line segment together. In other words, C times C equals A times A equals B times B. This formula can be rewritten to read C squared equals A squared plus B squared. You need to know, I have that formula highlighted. C squared equals A squared plus B squared. Everybody still good with the Pythagorean theorem? They go through some examples on how you can manipulate the Pythagorean theorem depending on what side of the triangle you're solving for. So they have the different equations right there. I don't know, right to the right of your highlight above 211 on page 7, they got the C squared equals A squared plus B squared. You can also have A squared equals C squared minus B squared, or B squared equals C squared minus A squared. So you can have those three different equations based on whatever side you're trying to find. The paragraph that's right after that, so second to last paragraph in the bottom left, last sentence is highlighted. As long as you know any two line segments, you can apply the formula and find the length of the third line segment. If you have, looking at that equation that's below or all the way in the bottom left, like they go through finding that, at the end, like if I have C squared equals 25, C squared equals 25. How do I get rid of the square?
Take square root.
I take the square root. That gets rid of that. Take the square root of 25. So I have square root of C squared equals the square root of 25. You just need to know that to get rid of a square, you do the square root. Good. On the right hand side of the page, I have the equation A squared equals C squared minus B squared. You're just going to have to solve for different sides of a right triangle. Page 8, 9 talk about how to go through on your calculator and punch this stuff in. I don't have any highlights on pages 8 and 9. (2:0) ratios between line segments going on to page 10. This is the section that's a little bit goofy. I didn't do the ratio stuff in school, but it's easy enough. Page 10, the last paragraph in the bottom left, I've got highlighted. It has been proven that in the case of right triangle, the ratio between the vertical line segment and the slanted line segment, hypotenuse, remains constant regardless of how big the right triangle is, as long as the degrees and angles remain the same. So after that, and on the right-hand side of page 10, I've got those 3 little paragraphs and the work below them highlighted. So, how is this useful? Again, referring to figure 14. So that's figure 14. They don't have.
I think you had it. You had it right.
Did
That's
I?
what Noah's was on. There you go.
Oh, there, I had it on.
Yeah.
All right, this is figure 14. So, if the ratio between the vertical line segment and the slanted line segment, so A over C, so whenever they say the ratio between the vertical line segment, that's always going to be A, to the horizontal line segment, which is C, that's going to mean A over C, is chosen to be 0.8 in decimal form. So that means 0.8 equals A1 over C1, or A1 over C1 equals 0.8. Now, if the length of either A1 or C1 is known, the length of the unknown line segment can be calculated. For instance, if A1 is equal to 6, formula will be read 6 divided by C1 equals 0.8. And then you can continue on with the math. 6 divided by C1 times C1 equals 0.8 times C1. 6 equals 0.8 times C1. You divide by 0.8 and your answer is on page 11. C1 is going to equal 7.5. It's ratios. It's super easy stuff. You are going to have, just take note that I do want you guys to do the questions for figure 13 when you're doing the section review. So maybe in the section review, just write in there, make sure to do the Pythagorean theorem questions on page 10. Oh, I do have, the last sentence on page 11 is also highlighted. As long as the angles remain the same, the ratios between the angles of the baselines and the hypotenuses in the 2 right triangles remain the same regardless of the lengths of the line. So as long as the angles don't change, the ratios are going to be the same. We're going to have section 2 review, flipping over to section 3. Right angle triangles and trigonometry.
Yay.
Some of the trade terms like complementary angles. Like these are some that you might have heard, but just need to review a little bit. Complementary angles are 2 angles that add up to 90 degrees. We'll talk about the sine, cosine, and tangent of angles. Reciprocal. I've talked about that whenever we do like the reciprocal formula for doing parallel electrical circuits, but that pretty much just means you're flipping, like if you have 1/2 and you took the reciprocal of that, it'd be 2 over 1. So it's just flipping a fraction. Sine, cosine, and tangents. 310. Second paragraph, first sentence is highlighted. The sine of an angle, pronounced sine and abbreviated SIN, is the ratio of the right triangle between the length of line segment opposite any of the length and the length of the hypotenuse. Anybody remember the saying for sine, cosine, and tangent is SOHCAHTOA? Yeah. So
This is funny. It says sine spelled with SINE, pronounced SIGN, and abbreviated SIN. That's the most confusing thing to ever put in a book.
So SOHCAHTOA.
Yeah.
So I got sine is equal to
Over hypotenuse.
cosine is
Adjacent over hypotenuse.
adjacent over hypotenuse.
And tangent equals over. No, so cut to over adjacent. Opposite and adjacent. I mean,
Is it opposite over adjacent?
yeah, opposite
Yeah.
over adjacent.
Yeah. The only one that's left.
And
So, OH. Oh. Yeah.
SOHCAHTOA.
there's A, adjacent. Instead of
Adjacent, yeah.
And then if you do the cotangent is the reciprocal of that. And,
Right.
yeah.
So all that's saying is if I have a right triangle and I want to know the sine of something. Say I want to know the sine of angle A. So they did say the line segments were lowercase, and then the interior angles are usually uppercase letters. So this would be side A, B, and C. So if I want to know the sine of angle A, you would take the opposite over hypotenuse. So it would be sine of A would equal B over C. Cosine of the angle. I've got the whole paragraph besides the last sentence highlighted. The cosine of an angle, pronounced cosine and abbreviated COS, is the ratio in the right triangle of the length of the line segment adjacent to the connected to the angle and the length of the hypotenuse. Same thing, if I wanted to know the cosine of A, cosine is adjacent over hypotenuse. So what side is adjacent to angle A? What two sides are adjacent to angle A?
That's A.
It's A and C, but C is my hypotenuse, so I have to use A. So that would just be cosine of A would be A over C. Everybody good with that? Moving on to page 13. The sentence that has complementary angles is highlighted. Two such angles, such as S and T, that add up to 90 degrees are called complementary angles. So for a right triangle, I always have complementary angles, right? Because I have how many degrees are in a triangle? 180. What is automatically one angle of a right triangle? 90. So the other two have to what? Add up to 90, which means they're complementary angles. The immediate next sentence is also highlighted. Therefore, the sine of an acute angle, what's an acute angle?
Less than 60.
Close.
Under 90.
Less than 90.
Oh, that's a 90.
Less than 90 is an acute angle. And a right triangle is always equal to the cosine of the complementary angle and vice versa. It's actually a pretty useful statement. So what that's saying is, if I had, therefore, the sine of an acute angle, so both of these angles are going to be acute, right? Because they're going to be less than 90 degrees. So the sine of acute angle, so sine of A is going to be B over C, and they're saying that, therefore, is the cosine of the complementary angle. So if I wanted to say my complementary angle is going to be, I'm going to call that B, so cosine of B is going to be, cosine is adjacent over hypotenuse. So what line segment's adjacent to B? B over hypotenuse C. B over C, B over C. Those are the same. Is all that's saying. Tangent of the angle, top right of page 13, the whole paragraph is highlighted. Tangent of an angle, abbreviated TAN, is another important ratio to angles. Tangent is the ratio between the length of the line segment that is opposite the angle and the length of the line segment that is adjacent to the angle. Figure 16, the tangent can be described as following. And I highlighted those two. Tangent of A equals A over B equals 5/12. Or tangent of B is B over A, which is 12/5. Moving on to page 14 and 15. You are, actually for this one, I'm going to pause the video back on. So continuing on.
Page 62.
320.
You sure, please?
What the heck?
We're getting there. 321, using tables to convert sine, cosine, and tangent values of angles. This is what our parents did, if they ever did sine, cosine, and tangent. They didn't have this in their. Like my parents didn't have computers in college and stuff. Like my parents went to college in the early '80s. Like they had a computer, but it was like Dad said it was in the library. It took up like this much room, and you had to run like cards through it. Like, yeah, we didn't have this, so they had tables for finding the sine of every angle. So my highlights for 321 is the first sentence is highlighted. One way to convert sine, cosine, or tangent values into angles is to use pre-calculated tables, like example 1. So that's one way of doing it. If you skip 2 sentences right after where you see appendix, I have the next sentence after that highlighted. The only limitation of these tables is that all the angles are whole number degrees, but not all sine, cosine, or tangent values are whole numbers.
You can still figure it out though.
You can still figure it out. It's just a lot of longhand math.
Yeah.
322, using a scientific calculator to convert sine, cosine, and tangent values to angles. I have used this in the field. I think it was something with conduit or I can't remember. I was figuring out an angle of something and I had to go back and use this math while actually, I think it was like one time, but I'd used it. Second paragraph of 322, first sentence is highlighted. First, decide what angle in the right triangle you're trying to find. Third paragraph of that sentence, or third sentence of that paragraph is also highlighted. Again, remember the sine, it's the length of the line segment opposite an angle divided by the length of the hypotenuse. Alright. Flipping over to page 17. They're going to, so whenever you are finding the angles, you are using the inverse of these functions. So inverse of sine, inverse of cosine, inverse of tangent. Okay? So just working through, before I give you highlights, just working through the left-hand side of page 17. I'm going to read that. I don't have it highlighted. Find the degrees of angle A. So find the degrees of angle A at figure 20 by applying the appropriate line segment ratio, sine, cosine, or tangent using a calculator. Because all line segment lengths are now known, any of the 3 ratios can be used. So if I want to find the angle of A, I'm using sine. Sine is what?
Opposite over hypotenuse.
Opposite over hypotenuse. So I have 17.4 over 26.8. Step 1, they go very slow through the calculator steps. Enter 17.4 in the calculator. The calculator displays 17.4. Step 2, push the divide key. Step 3, put 28.6 in there. Step 4, push the equal sign. And then that shows the sine of A is 0.64925. So that's what you just did, right? So you found that. Finding the degrees would be using the, let me just give you the highlight for it. I've got the sentence that has the word reciprocal, the blue highlighted reciprocal, and the sentence after it highlighted. The small -1 means that the process is reversed or inverted. The technical term for this reversal is called reciprocal. Sine -1 is the reciprocal of sine. So I've got steps the next steps 1 through 5 highlighted, and we're just gonna walk through those in order to find the degrees. Step 1, turn the calculator on. Step 2, enter. I would say everybody do this as we go, like just to make sure that you know how to do this. Enter 0.64925 into the calculator.
What are we doing? Finding degrees?
We are finding the degrees of A using our inverse sine function. So we entered 0.64925. Flip it over to page 18. Step 3. On this particular calculator, the sine and the sine minus 1 function are located in the same key, which is the same. If you still have your calculator that they gave you, it's the same for this. To switch from sine to sine 1, the key marked shift. The key marked second on y'all's calculator is in the upper left corner, must be pressed before pushing sine minus 1. By pressing the shift key first, the functions of the calculator change to those functions shown above the keys. This is similar to the shift key in a common computer keyboard. All calculators are a little different. It's important to practice, be familiar with the calculator, use regularly to build your confidence and reduce likelihood of entry errors. Step 4, press the sine minus 1 the calculator displays. That is not the one we're doing.
Don't you put it inside the parentheses?
Yeah, you have to put it in the parentheses. So you push second sine, which gives you sine minus 1, and then you input that number 0.64925, and you hit enter. Once you hit enter, you get 40.485 and so on. Round the answer to 1 decimal place. I prefer 2, but 1 is fine, so that would be 40. In mine, it would be 40.49 or 40.5, and that's how you get the angle. Is everybody good with that?
Yeah.
Alright. So continuing on, section 4. Applying fitter's math to tubing. So where could you use this in the real world?
Conduit.
Huh?
Conduit.
Conduit or tubing is what we're talking about for instrumentation. And these are real jobs that people are like. To be an instrument fitter is a job. Like you are a fitter that pretty much just does tubing and goes to plants and like tubes in new stuff. It is a lesser job, not a lesser job. It's definitely a lower paying job than like an instrumentation technician. So instrument fitter would, like I said, would just go in and do the tubing connections and stuff like that, because a lot of plants have a lot of tubing and stuff like that to go in and like a lot of these guys are working as like journeyman contractors that are going into new plants and stuff like that. You don't usually have. I could see PBF having like an instrument fitter on staff, but they also use
A lot of contractors, right?
they use a lot of I mean, they have like 80 triad contractors on site there all the time. So there's probably a triad. Triad is just a company that is a industrial contractor. So they have electricians and instrumentation techs, instrument fitters. So PBF could probably tell them like, we need a fitter for.
That's what we do over at Zadwin.
Yeah, just pulling in people.
My head went over.
What's that?
You said triad, I thought like the Chinese organization.
You use triad what?
When you said triad, my head
Oh,
went to
the-
the Chinese organization.
The mafia. Yeah.
I was like, the Italian mob?
First sentence on page 20 is highlighted. One of the most frequent applications of fitter's math is on the installation of tubing is when offset bends are required. These are the bends that you guys will be doing with Brian, the sweatshop guy, next Wednesday. Section 410, I just highlighted the heading, determining angles when side lengths are known. I highlighted the heading of that, and then you're going to have 3 questions, at least 3 questions come out of that. So if you know all 3 sides, then going and finding the angles and stuff like that is the second step. Top right of the page. First sentence in the top right is highlighted. When bending tubing offsets, fitters typically use any of the standard angles such as 45, 30, or 22.5 degrees. You pick what degrees you're using based on where you're running stuff. You want stuff to follow like the first highlight of the book, you want stuff to kind of follow the contours of what you're doing. So if I was trying to get over this piece of pipe, I would never use a 22.5 degree bend because it's going to take too long to get up this high. Like this is, they went in centimeters for some reason, but 45.7 centimeters, it would take a lot longer than using like a 45 or a 30 degree bend. A 45 degree bend is going to get up and over something quickly. Whereas in electrical, we had to worry about pulling wires through our bends and stuff like that. Tubing is going to have gas or liquid flowing through them, so it's not going to be as big of a deal to have more bends. If you need to get up and over something quickly, you can use a 45 to a 45 and you can get up and down quicker. Does that make sense? Yeah. Up and down quicker, rather than having, like the only time, like the times whenever you use like a 22.5 is if, like if you think about it, like if that's the ground, a 22.5 degree angle, like in order to get over like a 10-inch block, it's going to take a while to get up there and over and maybe back down. Whereas a 45 could go close to the ground, up, over, back down, and like you can just do it quicker. And you wouldn't want this hanging out there with all this space down here because somebody's going to trip over it or...
Technically though, wouldn't the 22.5 be less of a distance?
I don't know if it'd be less of a distance, but like you have...
Because think about it, 45 you gotta add that and that, versus the 22 you just add the hypotenuse, which is gonna be less.
It is, but like having all this
No support, yeah.
air gap, it's hard to support that.
Right, somebody's
because that's going to be at an angle, and even if you're
Oh,
doing something on the ground, like it's going to be hard to like find something to support that.
makes sense.
They go through the more of the calculator steps for finding the angles once you have the sides and stuff like that. But nothing else highlighted on pages 20 and 21. Flipping over to 22, first paragraph on the page, second sentence. It's pretty much the rest of the paragraph. Determining the length between the first bend and the second bend, the length of travel, which is also your hypotenuse. Measure, mark, and bend the first bend, then use the Pythagorean theorem and the calculator to determine the lengths of the slanted run. I have that highlighted. I have the Pythagorean theorem, again highlighted it there at the top of 22, c squared equals a squared equals b squared. And then step 2, down there below it, like talking about marking the second bend. They say, I've got step 2 highlighted. So lay the back of the original straight run of tubing on a flat surface, measure and mark the bent portion of tubing at 56.4 centimeters from the flat surface. And then the last sentence you key, like I have keyed in on, mark or make sure the mark is completely around the tubing. So that's important because like you'll bend something, you might have to flip it over and you don't know where your mark is. You don't mark it all the way around the tubing. A lot of times with contract, like if you're doing this like professionally, you're using a pencil. So that way, like when you're done, you can take your fingers and just wipe it off and it looks clean. I like Milwaukee markers. And do not care if the mark's on there or not. But pencil, like the professional, legit way of doing it is using a pencil so you can just wipe it off with your fingers or a rag or something.
Quick question. So like, why wouldn't you want to have just 2 90s in like that picture, for example? Is it just like preference?
I think that's
well, it says it's still not good enough, so it's probably gonna say 290.
Yeah, if you just go like straight up and then straight back on it.
Instead of doing 45, if we
Yeah.
just went straight to the wall.
To the wall of C.
Or straight to the
Yeah,
object.
and then make it 90.
I'll do it at 90.
Like that would just be up to the
90,
parameters of the
90.
installer, right? Like,
And
it wouldn't
I-
affect
It might
anything.
be hard to pull the wires.
There's no wires, this is
No
gas,
wires.
this is like air, either air or liquid.
Save that question for next week,
Yeah.
because I'd be interested.
Yeah.
Ask that guy, like, why, like, you're gonna be doing
Wires.
offset bins, and say something like that. So,
Right.
like,
I would assume even if it's not wires and it's gas and everything, it still creates some kind of resistance.
yeah, like we talked about the turbulent flow and stuff like that.
Go
So the
up.
more angles you have, you're gonna have turbulent flow, but if it's gas, it shouldn't
If it's
matter.
air, like usually most of the ones we have are airline, so like.
Yeah. Ask that guy, cause
Yeah.
I don't know. Yeah. If you are going through this, like I've got a lot of these long steps highlighted, moving on from 430. In 430, determining the side lengths when the angle is known. Not a bad thing to read through these steps. Like I know they're long, but it's decent to read through. I do step 2, first sentence is highlighted. Use an angle finder to read the degrees and the angle S as shown in figure 27B. Has everybody seen that? Y'all remember what the angle finder looks like? Like I had one for, I think when we were bending conduit. A little yellow thing that had a magnet on it. The degrees would change whenever you put it on something. So you can use an angle finder to find that. In step 5, on page 23, I have the third bullet point, the long bullet point in the bottom left of page 23. The gap between the two structures. So they like using this picture for some reason. But they're saying the gap between the two structures shown is 2 inches. So they're saying there's 2 inches in between here. You could subtract 2 inches from the 12 and bend the tubing to make the inside edge of the second angle fit snugly against the corner. However, it is better if tubing rests on top of the base structure for support because you cannot install tubing supports in the gap. For this reason, subtract the outside diameter measurement of the tubing from 12 inches to get the tubing to lay on top of the base structure, which in this case is ½ inch, resulting in the length of the adjacent side of 11½ inches. All they're saying is like if I'm bending a piece of tubing in here, I can't support it to this structure, so they want to support it on the bottom. So your measurement from here to here, you're just going to take that measurement and subtract the diameter of the pipe, which they're saying is ½ inch tubing. So from here to here, minus ½ inch is 11½ inches. And that way the pipe comes down, crosses down, and then lays on top of this. Does that make sense? Rather than trying to secure it to the top part. I have step 6 highlighted. To use the adjacent side length, find the length of travel of the hypotenuse. First, calculate the cosine of angle S. The side adjacent to the divided by hypotenuse. Then apply this decimal ratio in the formula shown. Because cosine equals the side adjacent divided by the hypotenuse, cosine S equals 11.5 over C, with C representing the unknown length of travel or hypotenuse. To solve for C, first multiply each side by the formula by S to separate them from the formula cosine S times C equals 11.5. Then divide each side by the formula cosine to solve for C. I also have all of step 7 highlighted. I think it's going to make more sense if you guys just read through that yourselves and start from step 1 and read through on how to find those angles based on the lengths of sides. And they show, like, I wish they would have put the picture on page 24, or this picture on the board. I might leave this picture up while you're doing this. So, like, I would read through those steps while you're doing this, because that's where, like, this is where I showed y'all, like, measuring from here to here is 12 inches, but then you're going to subtract ½ inch because you have ½ inch tubing, so this lays flat on that. Yeah, I would look at this while you're reading through those steps. been wandering through my lap.
Yeah, straight take it.
Straight there. I don't even know that shit. That's what I'm talking about.
Just go ahead and take it back.
Take it down. Not even do the views. Fuck the facts. I don't fucking know. Fuck.
Alright, moving on to page 26. And we're not. That's the end, that'll be the end of the recording. So I think